So, hello everybody. I'm Per Lindgren. Some of you might have seen me on the internet somewhere. Most of you don't, I guess. I work as a professor in embedded systems at LTU in Sweden, that is Luleå University of Technology. I'm also a guest researcher since a while here at TAU in Finland, here in Tampere at the university here, and involved with Henry and the SOC Hub team there. And I also work a bit with a company called Grepit, and one of my former PhD students, he started that as a spin-off from his research. And that company has now about 50 employees and doing EV chargers and other cool stuff. So that's about it. So this is my workload, 100% plus 20 as a guest researcher and 10 at Grepit. So that amounts to about 130% Rust. So that's me. I'm a Rustaholic, and I have a hard time letting go of hard problems and until they are solved. So spending a lot of late nights and having a lot of fun also in the meantime. So that's really my passion. Our research has resulted in the Arctic framework. It's like an operating system, but also not, because you are really having full control over the hardware. It's not like that you're giving up control to the operating system, but you can do everything. You can even write other operating systems in Arctic. And that is our basis for the research that we're doing currently. And the framework is quite popular with some 400,000 downloads over that. And it's open source and free to use. And it's based on a formal model. So you can actually reason about the behavior of the software running under Arctic or using Arctic. And it has been around for a while, in production since 2017, so there are products out that are still running the very first version of Arctic, and it was called RTFM at that point, but we changed the name on public demand. I still love the old name. It stands for real time. The RT is real time, and I is interrupt, and C is for concurrency. And we leverage on the interrupt controller of the hardware in order to get predictive and high performance scheduling. So it has caught on quite a bit since we started. And at least one next-gen ECU in a car ECU will run Arctic for the sort of coordinating of other ECUs in the system. Because an ECU, a car ECU, contains much more than just one CPU. It's a whole system. There is a huge community around embedded Rust, and we have some people here. So this is Asm and Lumpio. Is he here, or maybe he's coming? Maybe, let's see. I think he was enrolled. Isn't Henry Lumpio the other guy?
I'm not sure, sorry.
Okay, maybe he's coming later or not. So we work together with this community and try to look for their needs and see how we can meet the needs for doing development, and not only development, but also development that you can actually rely on. So it should be like that if it passes compilation, then at least what concerns scheduling of the system should be guaranteed. So it has this formal model and outstanding guarantees based on that. So there are no deadlocks. You might have heard of that in concurrent programming. That's a huge problem to avoid. and there can be no race conditions, and that's due to a combination of this formal model and the Rust language. So this would be much harder to do without the support of the language itself, or without the guarantees that the language gives us. So, is it perfect? Well, not really. There are still some escape hatches that makes it unsafe. And that is what we are going to talk about today. So that's my idea, at least. So a bit more on the Arctic framework. So we have Rust memory safety. You're all familiar with that. The theoretical model behind is called stack resource policy. It's not our invention. It has been around since the 1990s, but it requires that you do a static analysis of the whole task set, and that is not possible in typical C programming environments or typical operating system environments. So that's the reason why this model has not turned up more than it has. There are some use cases in automotive, not by us, but by others that are also using this scheduling policy to get these guarantees. But outside of that, there is nothing. It's declarative, so it's very specific. You define your tasks and what resources they should be assigned and how to access them. So we have this race-free execution, deadlock-free execution, and it's highly efficient because it utilizes the underlying hardware for acceleration. So we also have these Rust zero-cost abstractions, and that you are familiar with that. The compiler, the Rust compiler, compiles away all this layering of abstractions that you have in your code and make it into a binary that is highly efficient. And it's also highly predictive, so you can know when a task is going to be executed or who can preempt you. It comes directly from the model. And it's easy to analyze, so you can guarantee, for example, if you know the execution time, you can actually assert whether you will meet the deadlines if you have those specified. And that is not so easy using other operating systems. So this talk will be on safety mostly. But isn't it memory safe already? We have Rust, which is memory safe, and we have Arctic, which itself is also memory safe. But unfortunately not. Why is Rust not safe? That is because in Rust, we can have unsafe code, and that you might have come across, that you use a keyword, unsafe, in order to step out of the guarantees and the obligations you have to the Rust compiler. It's still better than C and C++, because these unsafe blocks are explicit, so you can vet the code manually. You can see that this code might be dangerous, and you can scrutinize it and try to prove to yourself that it's safe to do this. For example, we'll talk more about that when it comes to MMIO. But it's still up to the developer to assure this safety. So when does one use unsafe code? It allows you to use raw pointer dereferencing, and that is very similar to dereferencing of pointers in C or C++. So a const pointer would look like this, and a mute pointer would look like this, not with the ampersand, but with a star instead. Calling other unsafe code, like inline assembly, is unsafe. Calling external C code is unsafe, and calling other unsafe Rust. So you need to mark your code unsafe if you're calling into any of these. And it's heavily used for MMIO abstractions. In effect, you cannot reach the memory directly without unsafe code, and that is using this type of raw pointer dereferencing. And in some cases, you want to use it in order to convince the compiler that some optimization is actually possible to do. For example, internally to the standard library, there is some unsafe code for splitting arrays, where you can show that there can be no overlap between the first part of the array and the second part of the array. But to do that, it requires unsafe code, and that is due to limitations of the compiler. So what can happen if you write unsafe code, but it does not do what you want it to? Maybe you have a bug there, or maybe there is some malicious code there that, for example, wants to leak this secured key or something like that. So we can have security vulnerabilities, or we can have failures due to errors in this, or malicious unsafe code. And we can experience things like that we don't want, like these out-of-bounds array indexing leakage, and well, we can leak information in between tasks in Arctic if we use unsafe code. So we have some outsets from Arctic. That means that each task can only gain access to the set of resources defined in the declarative model. So you define a task and what resources it can use. But if you have unsafe code in task, it can do whatever. It can make a raw pointer to whatever memory location, including resources of other tasks. So, what if we can actually give access assurances in the presence of tasks using unsafe code? If we could do that, then we have already a very strong suit when it comes to safety and security using Rust and Arctic. But it could be even stronger, because there is nobody out there that can deal with unsafe code. That's, in effect, an unsolved problem. And we can make some other key observations here. That is that embedded Rust, when we program in embedded Rust, we typically use some type of structured MMIO. We are using some tool to generate the access patterns to our registers, which are mapped to some region in memory. So we already talked about this SVD to Rust tool. There are other, the RAL tool, the ship tool. They are very similar in that they generate APIs that dereferences these raw pointers. So these APIs will contain the sort of dangerous information, or the dangerous code, the unsafe parts. And then it gives a safe API for you to use, and these are proxies to the underlying hardware. And the way that these are implemented are using these zero-size types. So it's just when you are dereferencing the proxy, you're actually looking into the memory at that location that the proxy refers you to. And there is actually also a type for the proxy. So it returns a register block, and the register block has a size. So we know where it's going to point, because you have the ability to dereference it, and you know the layout, meaning the size of the block. This is interesting, right? So already from this, we have enough of information to know for each task in the system to which memory regions they should be allowed to refer. They should always be allowed to refer to their own stack memory, and besides that, to the resources. So there are no other sort of access areas for a task in Arctic. So it's either the stack or through some resource given to the task. So this is really, really interesting. We have now an abstraction that gives you exact information about the memory where a task actually can access memory. And if we can prove that this unsafe code is just referring to those specific regions in memory, then we're home free, right? So how would we do that? How? That is the question. But, well, this is more or less what I talked about. One possible solution to this is to use the Rust type system and define layout traits which can give you the layout for a given proxy or a given type, any type, and a get layout type that can give it for structured data. So this is for a specific, and this is for a structured data. And these can be implemented in as a template or implementation for all T, and a specialized implementation for deref types like these proxies that we were talking about. And then in order to use this, it's going to make a lot of, you have to write a lot of code manually unless you're using some sort of layout derive for the structures that you want to have this property, that you want to be able to inspect where they are pointing to. So I made a prototype implementation of this, and these are open source, and you can find them on GitHub, called layout traits and layout derive. And if time is given in the end of the talk, or maybe later after all talks, we can look into how the code actually looks like. Because it's not super difficult, but it's a bit more deep down in the Rust type system. So if we have this information, if we know for each task where it's allowed to point to, and we have a way now using these layout traits and the layout derives in order to do so. So what can we use it for? Well, one thing is for documentation. We can just automatically generate a memory map that this task is going to access these locations. That's useful information to the embedded developer. And maybe also for certification of code. We can use symbolic execution that does not run the code on the target processor, but instead it emulates the code behavior with unknown inputs. And if we can show that given unknown inputs, that the whole traversal tree, the possible path or feasible paths of this driver or whatever code you're inspecting is never going to touch anything outside these regions, then you know, and then you have a mathematical proof actually under the hood. These symbolic execution engines generate a logic expression that it uses solver to solve. And it's not enough time to go into details how this works, but we have done some research on it, and you can find that also on the internet. So this is a use case for symbolic execution to prove that the task cannot go outside of its specified regions. But that is then requiring some static analysis and so forth. But we already have hardware that can do it for us at runtime. So we have these MPUs, memory protection units. You might have heard of that. So we can set up the MPU, so when we are running a task, then the task is only allowed to run or access the memory defined in the regions that we have analyzed. So that will create a bit of overhead setting up the MPU, but it's affordable in comparison to chaos, which can happen if the code contains bugs or malicious code. So it's a huge thing regarding security and safety of the software to have this MPU. We are not the first one that are using MPUs, of course. Every operating system does that. But or not every, but this is a typical use case for MPU protection to sort of shield the user from using hardware memory or MMIO accesses, and just let the operating system do all the MMIO accesses for you. So it's not a new thing, but the new thing here is that we can do security by construction, meaning that we can actually already from the very beginning state that this task should have access to this resource and so forth, and then have a guarantee that the application will follow that, independent of how it's designed. So I think that is a very interesting thing towards safer and securer systems. So this is how it usually looks like, where you have an operating system and you have some code running in a trusted zone or trust zone. And I'm very much interested in speaking to or talking to and getting more information how this is done in like the ARM trust zone implementations. Is there anyone here that works with that or has experience with trust zone? A bit. We can have a chat later. This hasn't. So the point with this is that you set up a perimeter around the hardware and security critical or safety critical parts of the system, and let the user code outside of here contain whatever. It does not need to be trusted. But what happens if it tries to do something, accessing some I/O that it's not supposed to, then this perimeter will protect from intrusion. But the problem here is the same as with the 9/11 incident, that even if you have these security gates where you have to pass with your luggage and get X-rayed, it does not help if the problem is already inside of the perimeter, if the pilot is the problem. And that is the problem here, exactly the same. If internally the RTOS or any driver within the RTOS has malicious behavior or bug, then there is no secure zone. So ARM can say whatever they want, but there is no security unless this is fully correct. And in a real operating system like Linux, you have 10 million lines of code, and how do you even approach this problem? How can you trust like these 10 million lines of code to not contain bugs that breaks with this model? And one way of doing this is to prove that the operating system is actually correct. And there is a theoretical work around that. Cell 4 is an implementation of a kernel, an operating system, that is formally proven correct. But if you read their documentation, they say, if I run Cell 4, is my system secure? It's part of their FAQ, actually. And quote, not automatically, no. Security is a question of blah, 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 can be used in insecure ways. So that means that they disclaim any security at system level because the user code can use it the wrong way. Right. And so they spent like 10 years of proving Cell 4 to be correct. And in the end, well, it's up to you as a programmer to ensure that it's correct and correctly used. And I think that is super sad. But we can do better. If we have this, and we have the Arctic model for programming, and we have a tool that ensures that either at runtime or statically, that the code running adheres to the memory model given, then this is no longer a problem, or at least a much less severe problem. So what is the status here? Well, as of now, these have been implemented and tested, And we are trying it under development now on a RISC-V with PMP. It's a MPU, it's a memory protection unit with 16 regions. So that means that we could have 16 different resources for each task. And that is quite plenty. But we have also ways of coalescing neighboring regions and so forth that might make it possible to deal with larger problems where you have more regions than the hardware can support. But the PMP here is quite capable already. And that is existing on the C3 platform that you're going to use. So hopefully we can make some interesting labs for the students where they try to break memory security. So what remains? Well, we talked about HAL. And using HALs, you can sort of restructure the I/O or the MMIO accesses into new zero-sized types, into new proxies. And these needs to derive, if this works as we intend, the only thing that you would need to do is to derive this layout for these types that you're constructing yourself, and then be able to reconstruct the whole memory layout. So we haven't tested that, but it's on its way. We talked about symbolic execution. This is super interesting. We haven't done it for this purpose yet, but this is something that we want to do. And then we would like to make custom MPU protection with zero-cost task switching. As I mentioned, setting up the MPU when you're switching from one task to another involves writing to a series of registers itself. So it's a quite lengthy procedure. It might take like 50, 100 clock cycles or something. I don't know. We haven't done it yet, so can't really tell. But at least there will be overhead. But as with this SOC team here, we can build our own hardware. So why not build an MPU that can automatically switch from one task to another and using static configurations or even dynamic configurations? And I will just skim through the next two slides. This is a contributing idea regarding how one could implement this in hardware and also refine this to per task, per lock precision, meaning that a task, even if it's given access to a set of resources, it's not supposed to access these resources unless it has first locked them, if they are shared between other tasks. And then we would want the MPU protection to be dynamic. So at the point where you lock the resources, then it will sort of unlock your code in the way that it allows you to access this region. So once again, I think we need to compare this to the sort of state of the art, how it looks like in industry, where you have a single trusted zone and you have to trust the whole operating system. While in our case, we don't need to trust anything because we have memory protection per task and even memory protection per task per lock. So this is the huge difference in comparison to state of the art. So I think we can skip that also and get to the end of this. So ongoing activities, we have Henry here working on software. We have a guy, Antti Nurmi, working on hardware. So he might be interested in actually implementing this. We have some legal issues regarding ownership of ideas and so forth that we need to sort out first. But at that point, we might be able to actually demonstrate this on hardware. And we have me in Luleå, working both on software and hardware, and I have a master student that is doing the software for the ESP32C3 that you are using. So he will also prototype this MPU protection thing. So that will be the first actual sort of outcome of these ideas. So I thank you for listening. And also I thank Finland, because this was the first day here, and this is, I think, in Tauvo. Can that be a name in Finnish? It's sort of south of Oulu, a beach there. So we went kite surfing on Sunday, and after that we went to Lottaja for surfing there, and after that we made it to Ytteri, and it was so good. Really nice beaches and nice people. So we are really impressed. Maybe we need to move here. Who knows? So maybe we have a some question session, or
have you considered using some sort of compound pointers instead of MPUs to protect memory regions? So
No.
that the pointer itself knows about the region size and stuff?
No. But that could be an interesting alternative. But we haven't looked into that.
One of the safety issue is not just making sure that software only accesses the registers it's allowed to, basically looking at the memory addresses, but also that the registers are accessed in the right order.
Yeah, we don't solve that. It's not a full proof that the system is correct. It's just a proof that the system is not incorrect regarding the memory accesses. So using symbolic execution, you can get a much stronger proof of correctness, but then you need to manually annotate the assertions involved in the guarantees you want to give. In order to guarantee that this happens before that, you need to sort of state it as an assertion.
Right, you need to define which expected
Yeah.
order is
But
before you can check
that's
that,
not
of course.
actually Arctic as such does not look at all into the user code. So we are not doing any analysis at all regarding what you write in your programs. The only thing that we give guarantees regarding is when we are actually accessing resources in the system. So when we are doing that, we know that it's going to be deadlock-free and it's going to be erase-free and so forth.
Okay.
Is there any support for dynamic resource management, in particular memory management, across tasks?
No, I think that is where we have to put the limit, at least if we want to have it predictable, especially as we don't look into the user-written part of the code or the application code. And I think regarding high assurance systems or high security or high safety systems, typically these are smaller parts of bigger systems where it makes sense to have a static behavior and not allow for. We can allow for example, bounded dynamics in the sense that we are sort of analyzing the worst case. So we can have that, you can have sort of 5 instances or up to 5 instances of tasks doing something. But n number of tasks we can never deal with because it is a static analysis that we are doing.
Yeah, I have a question related to the formal proving of the system. Like you said, it's formally proven that if you have task specifications, they can't do this or that. But what if people intentionally try to break them? Do they cover that issue? Like there was the slide about the proven kernel that waives all proofs for misuse. Like, are there any cases for, like, I don't know, middleware or supply chain things that can come with that if someone is maliciously trying to abuse the task specifications?
I mean, regarding the resource handling and delegating access rights, if we have this MPU protection or having done static analysis, then no malicious code can make harm that way. So this is sort of watertight. So it can, of course, we're not giving any guarantee that when the driver or HAL implementation picks to write to this specific register, if that is illegally defined, if our outset is wrong, if the SVD, for example, points to the wrong location, such things we cannot deal with. But you will at least get the documentation telling that this is the memory regions that the software system will actually be able to reach.
Yeah, so you can verify that, without without being able to bury small details that are vulnerabilities.
Yeah. Exactly. So I still think that, well, you have to draw the line somewhere, and we have to trust that the SVD input is correct, because without that, what can you do? But on the other hand, we have the ability, since we get the footprint of the application, for some external party to go in and investigate, is this the correct memory layout? So that is outside our system, but still something that we actually provide. And that we can do already today. So.
Great, thanks.
So in order to define a task with specific resources, I guess you use some macros.
Yes.
And I wonder, how do you implement panic mechanisms? So each task can panic, and the user can define custom panic handler. So is it like another task for Arctic, or how do you define resources for the panic?
Okay, panics do not have any resources by themselves. And a panic in Rust, as you say, you can override the panic handler. And you can decide what it should do, if it should, for example, restart the system. That is perhaps the only sensible thing to do, actually, because there is no way to, in general, to recover from a severe error like that. And we have another interesting paper on avoiding panics that is using symbolic execution to show that your code, the paths in your code, can never reach any panic. So then you have a receipt that independent on the inputs, your code will never panic, even if the Rust compiler has inserted a panic because it was not able to prove it. So essentially, it works like this. Whenever Rust runs into undefined behavior, instead of just continuing working like nothing bad happened, it will always panic. That is the sort of good thing with Rust. So if we can prove that the code can never reach a panic, we also know that it's conforming to the Rust specification. So if that answered your question.
What is the, you mentioned the paper, what is the implementation? Maybe it's some crate or maybe?
Yeah, for that, we call the system cargo CLI, and it's a subcommand to cargo. So you can run that on Rust code and get a symbolic execution using the LLVM CLI tool. It's not perfect. There are cases where Rust makes assumptions on that data is initialized, for example, which can lead to false positives. And so we have to be a bit modest about what claims we can make regarding this cargo CLI tool. We have also, one thing here is that LLVM is sort of a moving target. There is changes and improvements going on all the time. And to keep a subcommand like cargo CLI working, we have to be up to date with all changes that is happening in LLVM. So what we have done now is, in a master's project, implemented our own symbolic execution engine. It's a bit more primitive than CLI. It also uses LLVM-IR, but we are not dependent on the IR C++ implementation or LLVM C++ implementation at all. And I think that is going to make it much easier to maintain and so forth. And we can also tailor the tool to do more Rust-specific analysis. For example, what we have there is a way to, when it comes to enum handling, if the variant field is not correct, then you will get a panic if you're outside of the defined variants in an enum. And how can we deal with that in a symbolic execution scenario? Well, we have a derive macro that is sort of making an assumption that the values are always within these bounds. And that makes it possible to analyze also enums, which is not possible using CLI.
Why I asked about the resource handling for panic is, for example, use case, if my task panicked, then I want to like blink an LED or display some text on the screen. So what is the proper way of doing this?
Well, using Arctic as it's currently implemented, there is no way of doing that. If you would do it, you would do it by just writing the code directly in this panic handler. You can do that. That is possible. But what we want to do is actually having, or one of the research interests is having a multi-mode system, so that if you are running into a panic, then you will run an alternative setting of the system that still uses resources and blah, blah, blah. So you would still have an Arctic system, but an Arctic system handling the situation where something has gone wrong. And it's not only the case where you run into a panic, but for example, if you lose connectivity to a sensor, well, if we're talking about automotive, the engine should still run, but not with the same set of parameters and control algorithms. So you should use another completely other controller. So to switch in between different modes of operation. And the same goes for low power devices. When you're running low on energy resources, when your battery is going low, maybe you don't want to do as much, but you will still want to live as long as possible. So to be able to implement mode changes into a sort of limp home mode or low battery mode, that is something we have discussed but not done yet.
Yeah, this is really interesting.
Yeah.
Thank you.
Thank you for the question.
Okay, so first question is about this. You said that there is way for the. Sorry, I'm panicking a bit, but yeah, but these tasks only have specific area of memory that they can touch. So it consists of the stack and the memory mapped I/O. So since we're dealing with these embedded targets, how do you prove that the interrupts do not touch any other region than those that have that you have specified for the current task?
Okay, very good question. So actually, interrupts and tasks are the same. So we have no interrupt handlers in Arctic. You are running instead of having interrupts, you have tasks. So you associate each task to an interrupt.
So you don't use any like hardware-specific interrupts, like let's say you receive some message through a I/O, or serial port or something. You don't use those registers. I mean the interrupts.
You do. You write your driver, if we call them driver, as the interrupt task. So that will be you write the code that should react to the event as a task connected to that interrupt.
Okay, that's clever.
So there is no overhead. There is no sort of thing in between you and the hardware. We just make use of the hardware in a clever way in order to give this resource protection mechanism. But essentially, an Arctic application runs as efficient or more efficiently than a bare metal application, because you, as a human, cannot figure out how these resource dependencies should be resolved. But the Arctic system does that, or framework does that for you. So it generates all the boilerplate code in order to make it safe. And it does that with some optimization. So it can use clever optimization algorithms in order to reduce overhead.
Okay.
Yeah.
So
one thing, though, which came to mind when you started your question, is that one problem that we have not touched here is DMA. So what if the programmer sets up the DMA, but it sets the DMA to the wrong region? So meaning that it will actually leak memory from one location to another. This is not solved by this MPU protection scheme, because the MPUs are not typically in the loop when the DMA is operating. So we have to think about that. That is one unsolved problem.
And the second question I've asked is how do you specify the common area that is used for, like memory section that is used for inter-process communication or inter-task communication in this case?
Yeah, that is part of the resources as well.
Okay.
So it's not only the references to MMIO, but you declare just the memory region that should be shared in between these three tasks, for example. And then this safe sharing is ensured by the Arctic framework.
Okay. And third thing I would like to say is that I think this kind of like, if we could have memory protection unit that is this like task aware, this would be really cool in a multi-core processor situation. So we could actually have like, let's say one core running just a, let's say Ethernet like driver, and one core running TCP/IP stack, and one core running an application, and there would be actually no context switching when running the application.
Yeah, that is doable. The Arctic framework is only a single core framework as such, but you can always partition your problem or your application into different domains and implement each of these domains using Arctic. And we are also supporting atomics for inter-process or inter-core communication.
About that memory protection unit idea, I don't think there is actually any hardware available today that can do that, like be a task aware to know like the memory map I/O.
That's why I say that we have to sort out some IP issues, because what I want is that it should be possible for publication. I mean, we are a researcher, we would want to publish this, but at the same time, I would want to protect the idea so that, well, at least you have a chance to be in the loop if it's going to be commercialized.
Yeah, thank you. Brilliant talk.
Awesome. Thank you, everyone, for your awesome questions. We're maybe a bit tight on time. How are we on time?
We are actually right on time, and we have margin left.
Okay. There was one hand raised still, so maybe we can take it quickly still.
I think we can take more questions still.
Great.
Coming back to the idea of multiple MPU settings, is actually not so uncommon. Maybe not in Cortex M or R, but Cortex-A and MIPS as well, I think, at least in the past, has this thing called address space ID. And you can basically...
I know that for the Cortex-M, they have this trust zone, which is sort of an additional MPU. So you have the operating system, you have the user mode, and then you have this secured mode that has specific privileges. What I'm after is being able to scale this to thousands of tasks with sort of configurable regions and have zero latency switching.
Well, I feel you could take some idea on how like in many CPUs, but not all of them have that. But basically, they have a similar problem in the sense that yes, you have a page table and you change the page table pointer, but of course, you don't want to like reload your whole TLB at every context switch.
Yeah.
So the TLB actually, besides the tag, also has an ASID. You change the ASID.
Yeah, they have the process ID.
Process ID. Call it address space ID or process ID, whatever you want.
It is a similar thing, but you will always run into the problem where you don't have enough of TLB entries, and then the TLB is like a cache, right?
Yeah, it is. Yeah.
So you will then invoke the operating system to bring in the right translations, and we want to do this completely in hardware. So we could give a proof or assurance that real-time behavior will not be affected.
Well, I mean, the hardware can also do the reloads themselves, and then, of course, even then you have undetermined latency, but I don't quite see it. I mean, you will always have some sort of limitation, right?
Yeah.
Even if you say I put like some hundreds of kilobytes of area,
of course,
SRAM area, there is a limit to how many regions you can have.
But
global.
Since we are using tasks or interrupts in order to schedule tasks, and we are interested in working with a RISC-V architecture, it has a limit to the number of possible interrupts. So in the standard, it has stipulated 4096 interrupts. So we thought that maybe if we can promote or if we can support that, and like in typical applications, maybe you will find 50 tasks or something that is a quite big system in our world. That's of course differs in between application areas, but for the deeply embedded part, I think we have quite static task sets, or in using Arctic we will have completely static task sets, and then you won't be facing problems with more than 4,000 of these. Okay, but it was a good question. We can talk more after the break here or during.